Today's lesson is on Ohm's law and Kirchhoff's law, two laws that look at the relationships between voltage, current, and resistance in series and parallel circuits. One of the first laws we look at is Ohm's law, and it looks at the relationship between voltage. A lot of times you'll see a triangle set up like this, V, I, R. And a real simple way to remember this relationship is twinkle, twinkle, little star, V is equal to I times R. Meaning if I want to get voltage in a component of a circuit, I need to know the current flowing through that component and the resistance of that load or that component. And then I could figure out the voltage drop across that. So it could be something like a resistor, which is what you see here. Or it could be a load like a motor or a battery or a light bulb, something like that. I can also solve for the resistance of a component as well. So if I know my voltage and I know my current, and I can rearrange this formula to solve for R, because I is multiplying the R, I just need to divide. So my R is going to be equal to voltage divided by current, and there we go. And if I could solve for current as well going through the circuit. So we've got a few questions here. This is the first one I want to take a look at, where we've got three batteries hooked up in series, and we've got a resistor in the circuit, and we want to know what the total voltage is in that circuit, as well as can we determine what the current would be and what would be the resistance. I've put a 10 ohm resistor in, and we've got a little animated simulator right here. So I'm just going to pop this all together, and we can actually watch the flow of electrons. And we can see that the electrons are flowing, all right, from the negative to the positive side. And we can take a look at what the voltage drop is across, or what the voltage pump up would be from all those batteries, because the batteries pump up the voltage. And we can see that it's 13 volts. Now, how do we get that? Well, Kirchhoff's law tells us that if we have light bulbs hooked up in series, that to get the total voltage, you just would add up all the voltages of each light bulb. So 3 volts plus 4 volts plus 6 volts, and that's going to give you 13 volts. All right, just like for question B, your total voltage would be 6 volts plus 6 volts, which would be 12 volts. All right, now I've got a 10 ohm resistor, and so if I wanted to, I could figure out the current. So my current, if I rearrange this, and what a lot of people do is they put their finger over top of the eye in the triangle, and they find that the relationship is voltage over resistance. It's just these triangles are just a simple way to figure out the formula for a 3-variable relationship. So if I plug in my voltage, which is 13 volts, and my resistance, I'll just double check here, click on there, yeah, 10 ohms. So my resistance is 10 ohms. Then my current should be 1.3 amps, because current is an amperage. And so we'll test the current right here, and sure enough, it's 1.3 amps, and it doesn't matter where we look on the circuit, the current is always the same, because there's only one path for the electrons to travel. All right, and what's interesting is if I punch up my resistance, say I bring it to 40 ohms. There we go. See, watch, the electrons move so much slower because there's more resistance. It slows the flow of electrons down. Now there's only 0.32 amps because my resistance is 40 ohms. If I plugged 40 into here, it'd be 13 divided by 40, which would give you 0.32. So that's one set of questions that we can look at. And then we've got another set of questions where we've got another type of circuit, and we've got 3 resistors hooked up in series. So we're going to take a look at what happens there. And in this case, what we're trying to do is solve for the potential voltage drop across each resistor, if we know the resistance on each resistor, and what the current would be throughout the circuit, and find those relationships. So just move this up top a little bit more. We'll take a look at how we want this set up, and we'll just really quickly here pull everything back. We will quickly disassemble the circuit and reassemble it to match what we see here. So I've got my light bulb, my resistor, and here's my battery. I'll just set up the exact same way that they have it. Rotate this over. Okay, this is one of the fun things about this. So this again is I'll put it back down to a 10 ohm resistor. This simulator works really nice. If you want to play around with this simulator yourself, you go to bit.ly/v circuit, and now that's just a short link to get to this. Let's break these guys up. So here's another resistor. This one's a 20 ohm resistor. All right, and then I'll put my 30 ohm resistor in right here. There we go. So I've got my resistors and my voltage. I need to bump it up to 6 volts. There we go, and that follows what the question is saying. So the voltage coming out of the battery, which would be the total voltage, would be 6 volts. So now what I want to determine is my voltage drop across each resistor. I know what the resistances are, and one of the things in terms of finding total resistance with using Kirchhoff's rules is that my total resistance will be equal to R1 plus R2 plus R3. So if I added up all my resistances, 10 plus 20 ohms plus 30 ohms, I'm going to get 60 ohms, and that's what I should get. So I'm just going to put 60 in here, and we're going to check out the math later. One thing I can do right now really easily is I can look at the current flowing through the circuit. So I've got 0.1 amps there, 0.1 amps there. Because it's a series circuit, it's always the same amount of current, 0.1 amps. So I can go ahead and put that in my current. So I've got that many amps going through the circuit the whole time. Now, what I would like to do is figure out the voltage drop. Now I can do this with math, or I can do this through the simulator. So through the first resistor, I get a voltage drop of 1 volt. Now let's see if this makes sense. We've got the resistance is 10 ohms. The current is 0.1. And how do we find V? Well, remember, twinkle, twinkle, little star, V is equal to I times R. So I1 is 0.1 ohms. R1 is 10 ohms. And 0.1 times 10 is going to be 1. For the next one, we've got 20. So the current going through at the second resistor, again, is 0.1 amps. Sorry, that should be an A there, not. So 0.1 amps, and we multiply it by the resistance, which is 20 ohms. When I do that, I'm going to get 2 volts. And we'll just double check. We'll pull our voltmeter across, get this out of the way because it's getting a little busy. And there we go, 2 volts. Now, if we can check right here, I'm sure we can guess what this is going to be. 30 times 0.3 is, 30 times 0.1 is going to give us 3 volts. And we can see that the voltage drop across each resistor, which we would add up following Kirchhoff's law, should give us 6 volts, and it totally does. The current stays the same. And if I want to determine what the total resistance should be, remember from up here, we found that we can find resistance by taking the total voltage drop and dividing it by the total current drop. So RT is equal to VT over IT. And then if I plug my values in, so I have a total drop of 6 volts. All right, and I have a current going through that circuit of 0.1 amps. 6 volts divided by 0.1 is going to be equal to 60 ohms. So we were able to make that work both ways there. Now the last question is a different type of scenario where we've got a parallel system, and the relationships are a little bit different for parallel circuits. So it's going to take me a quick second here to put all this together. So I'm just going to split everything up. All right, so I'm going to get my resistors sort of set up in nice order here. This is a parallel setup for my resistors. So I'm just going to quickly put them set them up like this and like this. And so now I can see that all my resistors are set up nice parallel orientation, and then I'll get my battery. Now, instead of doing a whole bunch of cells like that, I'm just going to do one. And I'm going to keep the voltage drop the same here. So if I go back to my table, my voltage drop is still 6 volts coming out of that battery. And I've got my 10 ohm resistor, and I've got my 20 ohm resistor, and I've got my 30 ohm resistor. I'll get these guys all lined up nice. And now I'll start to connect them. And we'll take a look at what the animation shows us. So we can see here something that's interesting. We can see the flow of electrons here along these two main lines is a lot faster than the flow of electrons around these. We can see that these electrons are moving faster, these ones are a little bit slower, and these ones are the slowest. Remember that we've got 10 ohms of resistance here, so a little bit of resistance, not a ton. 20 ohms of resistance here, so more resistance, which makes sense. The electrons would flow slower because there's more resistance. And then 30 ohms of resistance here, which would slow them down even more. And we can see that we've created this circuit here. So now we can take a look at some of the relationships. Let's look at voltage first. Remember, the electrons flowing through each path only have one load that they have to give their energy up to. And remember, voltage is the energy of the electrons. It's not electrical energy. In order to have electrical energy, you need to have voltage and current. So we can see that there's 6-volt drop there across that resistor, and oh look, 6-volt drop there across that resistor, and 6-volt drop there across that resistor. So in each case we have 6 volts. And again, that's because through each path there's no sharing needed. So my total voltage in a parallel circuit is going to be, in this case, 6 volts. And it's equal to the voltage going through path 1, the voltage going through path 2, and the voltage going through path 3. Now, if there were extra resistors within one of these paths set up in series, then sharing would happen. But because there's only one, there's no sharing, and so these electrons can give up all their energy to that one load right there. But what we can see, though, is that we have a different speed of current. And so we can look at the total current drop here, which is 1.0 amps. 1.1, sorry, amps. So my total current, I'm just going to write that in here, is 1.10 amps. Now, is there a way we could figure out the current going through each path and then check it to make sure it's correct? Well, of course there is, because I know that V equals I times R. So I is going to be equal to V divided by R. All I did was I just swung that R underneath the voltage, right? Just doing a little bit of math. So for the first resistor, we've got 6 volts divided by 10 ohms. And so what's 6 divided by 10? We're going to get 0.6 amps. All right, and so that is the current flowing through path 1. The current flowing through path 2 is going to be, again, our 6 volts, but this time we've got a resistance of 20 ohms. All right, so if this was 0.6 amps, 6 divided by 20 is going to give us 0.3 amps. And then the last one is, again, we've got 6 volts, and this time we have 30 ohms, and so we're going to get 0.2 amps. All right, and if we add 0.6, 0.3, 0.2 all the way up, we get 1.1 amps as our total current. So remember, for a when we're dealing with a parallel circuit, your total current is equal to the sum of the currents through each path. Now, the one weird thing is trying to solve for total resistance, because you can't add them all up. It's actually this weird inverse relationship. But we don't have to get into that per se right now. But what we can do is say, well, what if I want to find resistance total? I know that's my total voltage divided by my total current. And my total voltage is 6 volts, and my total current is 1.10 amps. And when I do that calculation, instead of getting a high amount of resistance, I'm actually going to get a lower overall resistance, 5.45 ohms.